make the concept even more clear to you. A parallel beam of light strikes at a solid surface of radius r. So you have again this time r radius globe. You can say a globe, you can say a glass sphere of radius r. It is made up of glass of refractive index 1.5. So it is made up of glass of refractive index 1.5 and a parallel beam is incident. So for parallel beam you will be infinite. There will be first refraction at pole P1. So let's see what happens when it is refracting first time. Rare to denser. Minus mu1 over u plus mu2 by v is equal to mu2 minus mu1 by r. It is a case of rare to denser. So mu1 is 1, u is minus infinite, mu2 is 1.5, v we want to get, mu2 is 1.5 minus 1 by radius of curvature, and radius of curvature will be plus r because you are going in the direction of incident ray. So 3 by 2v is equal to 1 by 2r. So v will come out to be 3r. So ये ray कहाँ जाएगी? This beam is incident parallel, and this is whole distance from P1 to P2 will be 2r. It means this beam is going somewhere for r distance behind the pole P2. But will it ever be able to reach there? Answer is no, because it's a now case of denser to rare. It's now a case of denser to rare. This beam will suffer a refraction from denser to rare. Yes, I1 will act as a virtual object for this second refraction. So here it's a case of minus mu2 by u plus mu1 by v is equal to mu1 minus mu2 by r. Mu2 is mu, but how much will be u? U will be this plus r. And mu2 is 1.5. Mu1 is 1. V2 we want to get. I call it V2. Second image, final image. 1 minus 1.5. And radius of curvature for this time pole P2 to center of curvature is opposite to incident ray, so it is minus r. So you get it here. 1 by V2 is equal to 1 by 2r plus 3 by 2r. So as I get 4 by 2r, you are getting it, and V2 will be r by 2. So the final image, what you will get here is at r by 2, not at r. जो फाइनल आपको इमेज मिलेगी वो r/2 के ऊपर मिलेगी. So it was again I must say a relatively easy question from the previous question on double refraction. But the new thing in this question with respect to previous question was it was a parallel beam of light that was incident at the first surface. So these three examples were the cases of double refraction. In first, it was not the double refraction, but in example number 8 and 9, they were clear cases of double refraction of a beam of light through a glass sphere. So these gave you a good insight, and they are important questions, believe me. Now we take this example number 10. It's a question just reverse of the previous question. In previous question, the beam of light was made incident, parallel from infinity, and then it was focusing somewhere. In this question, it's an IIT question. The beam of light is made incident from a point object and we want it finally to be parallel. So interesting question. A quarter cylinder of radius r and refractive index 1.5 is placed on a table. So just imagine this is the shape of a table and there is a quarter cylinder. Quarter cylinder is having its own radius r. So here is a center of curvature, here can be, you can take other point, and it has a refractive index 1.5 made up of glass. It is placed on a table. A point object is kept at a distance. So you have a point object which you are keeping at a distance mr from this. A point object is kept at a distance mr from it. Find the value of m for which a ray of light which is incident. So what is the value of m? For which the ray of light which is incident, it will first refract from rare medium to denser medium. So it will bend towards normal. And then it will go from denser medium. This is center of curvature. It will go from denser medium to rare medium. So instead of going here, it will bend away from normal. We want it finally to be parallel. Final image we want at infinity. So what is the value of m for this arrangement? So I take first case from rare to denser. So first is the case rare to denser. And when we talk about rare to denser, we call it minus mu1 over u plus mu2 by v is equal to mu2 minus mu1 by r. U will be in this case minus mr because first pole is here and it's a case of rare to denser. Mu2 in this case will be 1.5. V we want to get. Mu2 is 1.5. Mu1 is 1. Radius of curvature is infinite. The first radius of curvature. So it is 1 by mr plus 1.5 by v equal to 0. So 1.5 or 1.5 by v is equal to 1 by mr minus 1 by mr. So we get from here v, and that v comes out to be minus 1.5 mr. It means, I call it v1. It means this first ray will appear to come from, I take it with a different color. So this first ray will appear to come from somewhere here, I1. Now question is, if I1 is the image for the second refraction, is the object for the second refraction, if I1 is now the object for the second refraction, then how much is this I1 will act as an object for pole P2? So for pole P2, what is the distance of I1? So that it will act as an object for second refraction, which is denser to rare. So second refraction is now denser to rare. At pole P2, so it is minus mu2 by u plus mu1 by v equal to mu2 minus mu1 by r. Mu2 is 1.5. U for this will be, U for pole P2 will be, this distance is already 1.5 mr, minus 1.5 mr, and this is r. So this total distance from pole P2 will be minus, or minus can be taken out, 1.5 mr plus r, and mu1 is 1. Final V2 is infinite, is equal to mu minus 1. When we say R, center of curvature is here, you are going from pole to this, so it is minus R. So as a result, it is minus 1.5 by negative of 1.5 mr plus R is equal to 1.5 minus 1 divided by minus R. So we can say 1.5 R is equal to 0.5 into 1.5 mr plus R. So we can say 3 is equal to 1.5 m plus 1. So m is 2. 1.5 m is 2. 3 by 2. So m is 4 by 3. We can obtain from here the required value of m. So what should be the value of m so that the final beam is becoming parallel, that we can get from here? So this was a question well within your reach. आपने देखा, we have started from very simple question and now very comfortably you are even able to handle this question. Let's take example number 11. So now we take this example number 11, which is a good question, and it check your two concepts of a real and apparent depth and as well as convex refracting surface together. In part A, it is told you have a plano-convex lens of thickness 5 centimeter. So you have a plano-convex lens here and it has a thickness of 5 centimeter. And then there is an object, or maybe there is a point on this, its bottom. When you are watching it from this position, such that its curved surface is on the ground or on the table and it is being seen from above, then its image, its apparent depth is found to be 3 centimeter. So this is the first situation when you are watching it from through its plane surface. So its plane surface is above. This is the actual position of the depth, but its apparent depth is found to be 3 centimeter. What is the refractive index? So there we will use this basic formula. Apparent depth is equal to real depth by mu. Apparent depth is what? 3 centimeter. Real depth is what? 5 centimeter. Refractive index. So we can get refractive index as 5 by 3 of this plano-convex lens, or of the glass of this plano-convex lens. This is part A. Let's take part B. In part B, the same plano-convex lens is now kept inverted. On the same table, now the plano-convex lens is kept like this. We know its depth is how much? 5 centimeter. But this plano-convex is now kept reversed, such that now in this situation, if you have an object here and you are watching from above, its apparent depth is observed to be 3.5 centimeter. Now you know, this is a different case now. Question is, what is the radius of curvature of it? So it is kept reverse with its curved surface here. I call it pole P. I call it pole P. And the object may be here, but its image is found to be at 3.5 centimeter. How much is the radius of curvature? So you know, in the second case, it's a case of denser to rare refraction at spherical refracting surface. You want radius of curvature of this plano-convex lens. So I'll say it's a case of denser to rare minus mu2 by u plus mu1 by v is equal to mu1 minus mu2 by r. Mu2 is 5 by 3. U, for this pole, U will be minus 5 centimeter. Mu1 is 1. V is again here given as, it's not, we have this value of V. The value of V is given as minus 3.5 is equal to 1 minus 5 by 3 by radius of curvature is what we require. So if I solve it, it becomes 1 by 3 minus 1 by 3.5 is equal to minus 2 by 3r. So if I write this equation one further, I can take LCM 3 into 3.5. So I can write it here. I'm writing it here. This value becomes 3.5 minus 3 divided by 3 into 3.5 is equal to minus 2 by 3r. 3 get cancelled. So the value of r finally comes out to be minus 7 by 0.5 or minus 14 centimeter. Yes, you can understand the value of r here will be opposite to incident ray. If you are looking for the value of r, it will be, this is the pole and the value of r will be from pole to this point. The center of curvature will be towards down. So it is going to be negative. So it is minus 14 centimeter. And that's how you have seen these 11 questions. And by doing these 11 questions, you are now very confident about spherical refracting surfaces. Now we can move to the lenses from here.